Welcome to this final video on the FP1 Complex Numbers chapter. As usual, on the screen is a starter question to review the previous work. Pause the video now if you've got time and give this a go. And I shall go through it on the screen in red. Okay, we called this thing over here the modulus argument form of a complex number. That's because R is the modulus of z, also written like this, and theta is the argument of z, where there were some very particular things for the principal argument, which is that the principal argument always falls within this range here. And I said the best thing, in my opinion, is to sketch the complex number on an Argan diagram so you know where you are in terms of which quadrant you're in. So -8 on the real axis and 3i on the imaginary is over here somewhere. Well, this is 3 and this is -8. So the modulus was fairly straightforward. We can just use Pythagoras. And remember, we're squaring it. It doesn't really matter about the negative there. And if you do the square of 8 plus the square of 3, 64 and 9 is 73, and the square root of that is the modulus. So this is R. And we have to be a little bit more careful with theta, because this angle here is not the argument. Call this alpha, whereas the angle in white here is the argument. And to get the principal argument, we go, in this case, anti-clockwise, because if we went clockwise from the real axis, it would not be inside this range here. So let me calculate alpha first. Alpha is the inverse tangent of y, which is 3, over x, which is 8. And again, I'm not too worried about the negatives because I just want to find the size of that angle. The direction in terms of the angle is important for theta, not for alpha. If I bang that on my calculator, I get 0.358 ... Remember, don't round that yet. So to get theta, we've got pi minus alpha. Pi minus that answer was 2.78, and now I am going to round that. I'm going to round it to 3 significant figures. So in modulus argument form, we can say z, which is this thing in x plus yi form, could alternatively be written in modulus argument form as the square root of 73 times the cosine of 2.78 plus I times the sine of that same argument. And I noted that obviously this is a much simpler form compared to this, but there are reasons that we won't talk about just yet, but which you will talk about eventually, why this is a useful format to have. Okay, our second one, solve the complex rooted quadratic. And we can imply its complex roots because of the use of z as the variable instead of x. Now that's no guarantee, because you might find that you were expecting complex roots and actually they were real, or you were expecting real and actually they were complex. But the use of z implies a complex answer. So to solve this, we'll just go through the usual quadratic solving techniques. And let's do the formula, -2 plus or minus square root of 2 squared minus 4 times a times c. A is 1, so 4 times 12, 48. All divided by 2 times a, 2. So that's -2 plus or minus square root of -44, all divided by 2. Now I can split this into two pieces, so we've got minus 2 divided by 2 is minus 1 for the real part. And if I take this 2 and square it, so I can put it inside the square root, that'll be a 4. So that will be the square root of minus 11, which I can write as minus 1 plus or minus the square root of 11 times I, if I take the minus 1 out of the square root. And here we have our two solutions. Now to make it clear what these are, I've got z1, that is minus 1 plus the square root of 11 times I. Oh, running out of space. And z2 is minus 1 minus the square root of 11i. And of course they're very similar to one another. You can see why that happens because of the plus minus here. If you've got two real roots, usually you'll go ahead and square root this, and then by adding that number or subtracting that number, you end up with two very different answers, unless that's a 0, obviously. But with a complex number, what you're doing, you're adding and subtracting something that you're not actually going to combine with this section because it's imaginary and this is real. You're going to keep them separate. So you end up with the same real part in both solutions. And the imaginary part is either a plus or a minus. And hopefully you recognize these two in relation to each other. This is a complex conjugate pair. Z2 is the complex conjugate of Z1, or Z1 is the complex conjugate of Z2. And that will always happen, because you will always get this situation with a complex number where you've ended up a plus and a minus on the imaginary part, which is, if you remember the definition of the complex conjugate, you change the sign on the imaginary part and you leave the real part alone. And that's very useful. We'll talk about that in this video, because we're focusing on solving equations that have complex roots. And you might think, well, we just did that, and we did, but we're going to take it beyond quadratics. So, notes first. If a polynomial, now that's important, this is not all equations, this is polynomials. And it has to have real coefficients. We're not going to get into complex coefficients at any point in this course. So if a polynomial with real coefficients has a complex root, z, then it must also have a complex root, z star. Like we had on the previous example, if the z comes up as a root, the complex conjugate of that root will also come up because of the plus minus on the square root. Complex roots in polynomials always appear as complex conjugate pairs. Now this is saying pretty much the same thing, but it's common to see it phrased like this. And again, that's very useful. We'll see some examples later in the video where this really helps us. So if the roots of a quadratic equation are alpha and beta, what I have so far been calling z1 and z2, so these are complex numbers and these are the roots of an equation, then you know from your previous work that you could effectively factorize the quadratic into two brackets using those two roots. So z is the general variable that we're using, minus root 1. Whether you call that alpha or z1 doesn't matter, but because the textbook uses alpha and beta, I've used it here. So z minus root 1 times z minus root 2 must equal 0. And you know that from your factorizing work. And if you expand that out in the usual way, you get this. And this will be the complex rooted quadratic equation that these two roots are from. That might seem strange to do that, but it is worth noting that because of something else you already know, that if in general z is equal to a plus bi, then z plus its own conjugate we know is a real number 2a, because the imaginary parts cancel out. And z times its own conjugate you end up with a real number a squared plus b squared. Because again, when you multiply these, a z and its own conjugate, your imaginary parts disappear. Connecting these two then, if you have a look here, z plus its own conjugate. Well, if alpha is a complex number and beta is a complex number and they're both solutions of the same equation, they are conjugate pairs, as we saw just at the beginning of the video. So here, alpha plus beta is doing this. It's a complex number plus its own conjugate. So you could say straight away, if you know what alpha is or you know what beta is, you could find out what that coefficient in the original equation is just by doing 2 times the real part of your root. Similarly here, z times its own conjugate is happening here, because alpha and beta are conjugate pairs. So if you want to know the constant in the original equation, you can apply this with one or the other of your 2 roots. So that's useful, and again we'll see in an example later how that's useful. Okay, so let's get into some of these examples. Given that alpha equals 7 plus 2i is one of the roots of a quadratic equation with real coefficients, state the value of the other root. Now we know this straight away because of what we've just been saying. If this complex number here is a root, then the complex conjugate of this must also be a root. So that must be the other one. So beta must be 7 minus 2i. So you can see how useful that is. Once you know one, you know the other directly. That is not true for real roots, but for complex roots, it is. Part B, find the quadratic equation. Okay, that's applying what we did on the previous slide. So if you've got z minus alpha and z minus beta, these are the 2 roots, then that will equal 0. So just expanding this out will give me the equation. So if I've got z minus 7 plus 2i here, z minus 7 minus 2i here, then I've got z squared by multiplying the first 2 terms of each bracket. And then when I get to this times z plus z times this, I end up cancelling out my imaginary parts and doubling up my real parts. So I end up with minus 14z. And that's the minus 2a coming in. And you can go through that if you want, just to confirm for yourself that that is true. The final term, this multiplied by this, and again that gives us a real number of value 7 squared plus 2 squared, which is 53. And if that's gone too fast, then please do pause the video and multiply those and just confirm for yourself that this is true. Another way to confirm it is to put this equation on your calculator, let your calculator solve it, and show that indeed these are the 2 roots for that equation. Part C. Find the values of alpha plus beta and alpha times beta. Well, if we go back to the original alpha here and beta here and just have a quick look, alpha plus beta, 7 plus 7 is 14, 2i minus 2i is gone. We get alpha plus beta is 14. And again, that's why that number here is 14. And then alpha times beta, if you multiply all of this out, you end up with 7 times 7 minus 4i squared, which becomes plus 4, so we've got 53. And then 7 times minus 2i is minus 14i. 2 times 7 is plus 14i, so they cancel out. And again, we'll come back to this number 53 here. That's the reasoning why these numbers come up. And it says, and interpret the results. Well, I'm not going to write a sentence, although that's what you would be expected to do, but just talking through, this is the coefficient, or minus, this is the coefficient of z, and this is the constant in the equation. That's what this example is trying to get you to realize. So rather than actually going through the process of multiplying all of this out, if you just add these two and multiply these two, you know these terms here. Okay, I hope that was okay, because that's sort of a culmination of everything that we've done up to this point. But now we're going to push it into cubic equations, again with real coefficients. That will always be the case. So cubic equations, we've got a cubic term, potentially a quadratic term, potentially a linear term, and potentially a constant. Obviously this one is the important one to make it cubic, but we're going to assume a general equation. And of course all these x's will be z's if you are expecting a complex root. Okay, so that's what it is, but in terms of your notes, cubic equations with real coefficients have either 3 real roots, and they can come up in different sorts of ways. They might all be the same, might be 3 repeated roots together, and graphically that would look something like this. Or you might have 2 repeated roots, or I guess 1 repeated root and another root, or you might have 3 distinct roots like this. But in all of these 3 cases you end up with 3 real roots. But from what we've just said, you might have a complex conjugate pair. And because these always come up in pairs, conjugate pairs, you will also have 1 real root. So you cannot have 3 complex roots because they must come up in pairs. So here, for a cubic equation, you can have a maximum of 2 complex roots and a minimum of 0. You can't have 1 and you can't have 3. And graphically, what this is relating to is something like this. And hopefully you can convince yourself very quickly that you will always have 1 real root, because for any cubic equation it must cross the x-axis eventually. And here are where your 2 complex roots are coming in. So these are your 2 options, either 3 real roots or 1 real root and a complex conjugate pair. There's no other option with a cubic equation. Let's do a quick example. Given that -1 is a root of this equation, find the value of k. Okay, so obviously as we're talking about these fairly complicated things, don't forget all your basic understanding from previous years as well. If we know that -1 is a root, we can just put it into the equation and it must equal 0, and we can do it that way to find k. So we've got -1 cubed minus -1 squared plus 3 plus k must equal 0. So just by substituting the root they've given us into the equation. That's -1, that's a 1, but there's a minus in front, so that's a -1 plus 3 plus k equals 0. So k must equal -1 as well. So now we know the equation, z cubed minus z squared. 3 minus 1 is plus 2. So this is the equation. And part B wants us to find the other 2 roots. So we want to solve this. Now solving cubics, what you've probably done in the past is to factorize out a linear term and then have a quadratic bracket that you go on to solve separately. And that's what we're going to do here, because again, they've told us what one of these roots is. So if we know that minus 1 is a root, then we know that z minus minus 1, or z plus 1, is one of the brackets when we factorize. So we are applying the factor theorem. So let's have z plus 1 times something z squared plus something z plus something equals 0. Alternatively, you could divide this equation using polynomial long division divided by this, and that will get you, hopefully, the same answer that I am going to get here. And I'm doing it this way just because I can see 1 times c must equal my constant 2, so c must be a 2. Z times az squared must equal 1z cubed, so a must be a 1. And then to get no z's, we don't have any z's here, so let's look at z. Z times c, which is 2, that's 2z, plus bz must be 0, so b must be a minus 2. If you followed that, great. If you didn't follow that, you can divide this equation by this bracket and get the same answer. And the answer we get here is z squared minus 2z plus 2. And of course, if you've got time, you could expand that out and just check that you get back to this equation here. So we know that this gives us the root z is minus 1, that's the one that we were given. But now we need to solve this thing equals 0. And I'm not going to go through the process each time because that's not the purpose of these examples, so I'm just going to quickly put that onto my calculator here and let my calculator solve it. Keep in mind though, in an exam setting, you need to show your process. So let's call this z1, z2 is 1 plus I, and z3 must be 1 minus I. Yes. So here are the three solutions, and we have a complex conjugate pair and one real root. Okay, pushing it a little bit further. This is as far as we're going to go. Quartic equations. Now, quartic equations, I hope you know, are power 4. So that's the important term. But again, talking about a general one, you have to allow for a cubic term, a quadratic term, a linear term, and a constant. So this is the general quartic equation. And again, we're talking about real coefficients. At no point should you have to deal with complex coefficients. That is beyond the scope of this course. But these are a little bit more complicated in what you could get. You could, of course, get 4 real roots. And you might have, you might have them all exactly the same. There might be a repeated root on every one, or you might have 2 pairs of repeated roots, or a repeated root and 2 distinct roots, or 4 completely distinct roots, and that all corresponds to the various graphs that you might be able to get. Things like this with a quartic. But you might get a complex conjugate pair. Abbreviate that there, complex conjugate pair and 2 real roots. And that will correspond to something, for example, like this, where if you forgive my use of language, this little wiggle here does not cross the x-axis, there's your complex conjugate pair, and this wiggle does cross the x-axis, so you get 2 distinct roots, or perhaps it only touches the axis, in which case you get a repeated real root. Or you might get two complex conjugate pairs. And that, unlike the cubic, would correspond to the graph not crossing the axis at all. And you get a complex conjugate pair here and here. And no real roots. But again, like the cubic, you can't have an odd number of complex roots. They come up in complex conjugate pairs. So either you have two pairs, or one pair, or no pairs. Those are the options. It is worth noting, however, that just as with the real roots, you could get a repeated complex conjugate pair. So a quartic equation might look very similar to a quadratic, just like this one over here did. And that would correspond to a complex conjugate pair that was also a repeated complex conjugate pair. I hope these graphs are not making it worse, but are making it better. So you've got three different options here: 4 real roots, 2 real roots, and a complex conjugate pair, or 2 complex conjugate pairs. But the key point again is that the complex roots come up in conjugate pairs. They must do, and they always will, for polynomial equations with real coefficients. Okay, a couple of examples to finish, and then that is the chapter done. Given that 3 plus I is a root of the quartic equation this, that's pretty heavy duty looking, solve the equation completely. Okay, so these are getting slightly more involved examples. Might take a little bit of time, but they're telling us one of the roots. So let me call that Z1. Now what that also tells us is Z2, which must be the complex conjugate of this. So now I know 2 roots, which means I can start to do my factorizing. And that would leave a quadratic equation. Because if you expanded all of this out, you would get back to a quartic. I know Z1 is this, so I know Z2 is this, and I don't know this yet. I have to allow it's a general quadratic. It may not have a B, it may not have a C, but it will have an A. And I need to figure out what these 3 coefficients are in order to then solve this. These 2 already solved. And to do that, I'm going to put these in, here and here, expand this out, and then compare this expanding with this to ensure that the numbers would all match. Although again, once you've expanded these 2 together, you could take this beast of an equation, it's a bit of a beast, isn't it? And divide it by the quadratic that you get here, and that would give you the same answer. Okay, so let's go for it. Z times Z, obviously, Z squared. Now, the Z times minus Z2 and the Z times the minus Z1, we said that is going to use 2 lots of the real part, and it's going to be a negative. So I'm going to have a negative 6Z. And if that's jumping too quick for you, take the time to do this. Put this in here, and just go through the expansion. Oops. And make sure that you're getting the same answers. Same here, the minus Z1 times minus Z2. If you're not completely sure how I'm going to get this number, go through the process. But what I'm going to do, I'll get 3 squared plus, from this part, 1 squared. 3 squared plus 1 squared is 10. That's going to be a 10. Using what we talked about with the alpha and beta near the beginning of the video. And like I said, you could take this quartic and divide it by this quadratic to get the answer for these coefficients, but I'm going to just compare, if I were to expand it, what I would need in order to get these coefficients here. In all of this expansion, 10 times c is the only constant term, so that must equal minus 50. So my c must be a minus 5. Similarly, this z squared times a z squared is the only z4 I'm going to get out of this expansion, so my a must be a 2. B is always the slightly more difficult one because there are going to be more than one way to get a z. So if I was going to expand all of this out, let's look at the z terms. So it would be 10 times bz. Let me just put that up here. So I'd have 10bz would be a z term. But I would also have minus 6 times cz. I've already figured out that c is minus 5. Minus 6 times minus 5 is 30z. So that would be a plus 30z. And these two terms must add together to make 120z. And that's a fairly simple equation to solve. Looking at the coefficients, take this over here. That gives me 90z. To get 90 from this, b must be a 9. And again, if you followed that, great. I think personally it's a little bit quicker than doing the long division. If you didn't, that's fine too. Go through the long division and you should get this same solution with no remainder. So this equation in green is the same as this, only it's now factorized into two quadratics. I don't need to solve this one because that was already solved from the information we were given in the question. This one is done. But I need to solve this one to get the other two roots. So what we're focusing on is this. In an exam, you would have to then show your process, show the quadratic formula with the numbers inside it, but for the sake of time, I'm going to just put it on my calculator. And the answers are not complex, half and minus 5. So Z3 is a half, and Z4 is minus 5. And don't worry about the fact that these are real using a z, that's fine. It's just convention to use an x if you know they're all going to be real. In this case, they weren't all real, so z is fine. Don't worry about that. So here are the four solutions. 3 plus I, 3 minus I, half, and minus 5. And if your calculator is good enough, in terms of polynomial equation solving, you could put this equation on your calculator just as a check that you've got the correct solutions. In terms of an exam setting where you just want to be careful that you haven't done a silly mistake under the pressure. Final example, and then we'll finish. Show that z squared plus 4 is a factor of this quartic equation. Hence, that means using this fact, solve the equation. This equals 0. You could say that there are two ways of doing this. You could solve this, put one of the two solutions into this equation and show that it does equal 0. But this is a case where the polynomial long division, this divided by this, is a much easier and quicker way of doing it. That also gives you information that you will use in the next part as well. So it's definitely the best way to go on this question. So that's what I'm going to do. We've got the quartic equation here. And we are going to divide this by the factor we've been given. In order to show that it is a factor, we need to have a remainder of 0. So I hope you can remember how to do this. Z squareds into z power 4s gives us a z squared, times that by the factor on the side, z power 4, and I'll just write 0z cubed to keep my alignment correct, and then 4z squared, and then the other two are zeros as well. And then we need to subtract all of this, and we get the power 4s go away, minus 2z cubed is still there, Now we have 17z squared and minus 8z plus 68 is still there. And then we go again. How many z squareds can we get into minus 2z cubed? We've got minus 2z of those. Times that by our factor, we get minus 2z cubed. In this case, we have 0z squareds minus 8z, and we need to subtract all of this. That gives us 17z squared still. The 8z is gone, and we still have the 68. How many z squareds in 17z squared? Well, we get 17, and hopefully this will be the last round. 17 times z squared is 17z squared, and 17 times 4 is indeed 68. And when we subtract that, we have a remainder 0. No remainder. Therefore, we can say with confidence that z squared plus 4 is indeed a factor of the quartic. So we've done the first part, but we've also done most of the work for the second part, because this here, the result that we've got from the division, is the other bracket when we try to factorize this quartic. In the next part, put it equal to 0. We've got one bracket already given to us, and the other bracket we've just found. And we know that this is equal to this expression here, and so we just set that equal to 0 in order to solve the equation. And as with the previous example, I won't go through all of the method that you should go through in an exam, just to save time. This one's quite easy. We know that that is going to give us a plus and minus 2i, and this one you should put into the quadratic equation, but I will just use my calculator, and that gives me the result of 1 plus or minus 4i. So if I make it very clear, we've got z1, 2i, second root, minus 2i, third root, 1 plus 4i, and the fourth root, 1 minus 4i. So here we've got two pairs of complex conjugates. And by now it should be no surprise that we've got 4 roots to a polynomial of order 4. Polynomial of order n will have n roots, although of course you have to allow for the fact that some of them may be repeated, so it may seem fewer when you write them out. And that's it, the end of our final example. That was quite a long video compared to some of the others in this chapter, but now you can practice using questions from exercise 1H and 1I for the content of this video, and for the whole chapter, the chapter review exercise. And maybe I'll see you for chapter 2.